Okay. So I'm going to start with part 4 actually, and just kind of show you how you were supposed to work through that. There's obviously multiple ways for any synthesis one, but basically for both of the starting materials, you'll have to do something. And so looking at the final product, you basically first of all have to turn this one into a diene. And so to do that, what I would just do is treat this with tert butoxide twice. And what that can end up doing then is it makes basically just 2 elimination reactions and allows you to have a diene. So this is all you need to do with that first material. The second material then looks like this. And so looking at, all you'll have to do for that is you'll basically need to oxidize it as one of your first steps. The reason for that is how the product is written, how that substituent works is you have a CHO group. What that means is that's the same thing as basically an aldehyde. So I'm going to do is treat this with PCC. You could really do anything that oxidizes it. What that gives you then is something that looks like this. And so then these would be your 2 reagents. You put those together, and with Diels-Alder, they will form the desired reaction. So that's basically all you'd have to do for part 4. And once again, feel free to stop me if you have any questions. Let's see, we'll do part 3. Okay, so for this one, basically you're just treating it with light, and the compound looks like this. So the trick is, remember, anytime you treat something with light, you're going to actually use that LUMO state instead of HOMO. And so just thinking about what that's going to look like, if you have, I'll draw out what that HOMO state kind of looks like first. So just in this part, you're basically going to have 2 nodes in the HOMO state. So going to look something like this in the HOMO state. When you excite this with light to LUMO, basically, as long as you drew something that has 3 nodes then instead of 2, you would get credit. Oh, I saw there's a question, sorry. So on the dibromos, yes, you could use NaH. That's also a strong base. So doesn't matter, anything that will do elimination. You need to check the chat more regularly, sorry about that. But yeah, so this has 2 nodes. Once you excite it to the LUMO, it's gonna have 3 nodes. So as long as you drew something with 3 nodes, the main thing that's gonna happen once you do that is looking at the end ones. They're actually gonna end up being opposite each other now in that state. So if you do something like this, I believe you get full credit as long as you know that these are opposites. Drawing how this is going to react then. So basically, you're just going to draw, I'm going to draw this kind of head on. So it looks like this. And so drawing, we'll just use this example of the LUMO that I drew. So you'll have this, this, this. And basically how I drew it, it'll look like this. And it also had these methyl groups coming out on either side. And so basically, in order for these to combine with each other to make that sigma bond, basically what I'm going to do is I'm going to rotate this one this way and this one also this way. So that would be conrotary. What that's going to do then is if you rotate this methyl group's going to be facing up now. This one's going to be facing down. And so what the products you could have then are so you have this. Let's see where there's going to go. So you'd have this product, and then you'd have its enantiomer, would be the products you would get. And as long as you drew it, so these are going separate directions, so one is dashed, one's wedged, you would get full credit for that. Are there any questions on this one? Okay, cool. Then let's see what else. I'm gonna look at some of the multiple choice part. If you guys would like, I can go over part 2 for the exam. Just let me know. Otherwise, I will. I think it's a little better use of time to go over the multiple choice part. So let's see. So for number 1, at least at the example I'm looking at, so all of you may have had slightly different questions. The delocalized pi cloud of benzene, that one should be located above and below the plane of the ring. The reason for that is, as you can see, so if you have a benzene ring like this, I'm just going to draw it so it's kind of almost looking at it from the side. How this is going to work, remember, so how the pi orbitals look is they're going to go down and below. So as long as you said that they were above and below the benzene ring, you get credit for that. It is a planar molecule. One of the questions asked, which is accumulated diene. The accumulated diene is going to look something like this. Remember, accumulated is where the same carbon has 2 double bonds. That's really unstable. That's one you should have put there. Let's see. So one of them asks for 2 possible products when you treat this compound right here with Br2 and dichloromethane. And so how that's going to work is basically, if you think about how this adds, you're either going to have the 1,2 adduct or the 1,4 adduct. And so I'm not going to write out the mechanism for this one, but remember, I guess I'll just kind of show the gist of it. You'll basically have the bromine. Let's say it attacks here for the first one, puts a carbocation here. So the bromine, the next bromine could either add here, or you could have resonance come here, and then the other bromine could also add here. And so what the products you're looking at then are going to look basically, you could have this, or you could have this. And there you go. So these would be your 2 potential products for that. The next question asks for the kinetic product of the following. Remember, so kinetic product is what's favored when you don't have rearrangement, so at a lower temperature. And so what this problem asked for was you basically just had this compound here. And it was treated with HCl. And so how this is going to work is it wants to form basically the carbocation at the most substituted position, which in this case would be right here. So what's going to happen is these will attack the hydrogen and make it so you basically then have this with the methyl group still there, but now this is a carbocation. The chloride ion that formed from that is then able to attack that carbocation. And the product you would look for then would be this. Okay. Moving on. So this next one, almost everyone in the class actually got this wrong. And so the question is just, you're supposed to say if it's planar, is it anti-aromatic, non-aromatic, or aromatic? And so let's see what it looks like. So it's a 7-carbon ring. So something like that, and how they drew it was like this. And so how this is going to work is, remember, to determine aromatic or not, you're just going to look for delocalized electrons. And how this is going to work then, so you have 1, 2, 3, 4, 5, 6. In order for this to be planar, we're going to assume that this is already going to be sp2, with this being a delocalized pair of electrons. So that means we have 8 total electrons. If you look at the 4n plus 2 rule, this is to determine if it's aromatic. If you make this equal 8, you end up getting that n has to equal 1.5. So it's not aromatic. What you can look at then, though, is, so for the anti-aromatic, it's just 4n equals 8, n equals 2, which is an integer. So this one is actually going to be anti-aromatic, will be the answer to that one. As I said, that almost everyone got that one wrong, so don't feel bad if you got that, but that is just basically using Huckel's rule. You could figure that out just by plugging in those values. If you got it, nice job. Let's see. Once again, feel free to stop me if you have any questions. If not, I'm basically just going to go through this exam and kind of explain what we're looking at. So yeah, I guess another one is just a basic Diels-Alder question, and it wants you to draw the major product, or I guess pick the major product. And so these are the reactants. And so remember, when this undergoes Diels-Alder, all that's going to happen is that's going to form a double bond, or a sigma bond there. That forms one there. Your overall product then forms that 6-membered ring. And for the major product, you're going to want the endo form, which would be both of these dashed. So that would be the answer you want there. Most people, it looks like, got that one right. Let's see, there was one that had these 2 reagents. There's just a lot of Diels-Alder in a row here, so sorry if this gets kind of repetitive. So we have this plus this. So you have those 2 things. Basically what's going to happen is whenever your diene is a cycle, remember, you're going to form a bridge. So what this will end up looking like, if you position it kind of, I'm going to just rotate this in space. So this will be the diene. This is the dienophile. How this is going to work then, if these do their rearrangement, you're basically going to have a 6-membered ring. With, since there was just 1 carbon here, you're going to have a 1-carbon bridge like that. And then looking how you'd expect the carboxylic acid groups to arrange themselves, since it's going to be the endo product, we'd assume we're going to prefer, we're going to make both of these go down. And so we can put these like this. This is the same thing as if you just drew them dashed. But either way, so your overall product then is just going to be, in this case, G was the correct answer for what I'm looking at, and it just has that one bridge with those extra groups headed downwards. Anyone have any other questions before I keep moving on? Okay, I'm gonna skip a bunch of the Diels-Alder ones because I do think they're kind of repetitive. And it looks like based on the stats that most people are getting most of them correct. Trying to see if there's any that a lot of people got wrong. Okay, this one, a decent amount of people, it looks like, didn't mess up on. So I am gonna just draw out what this looks like. So what's this ask for? Select the endo product. And if you select two products, write the letters separated by a comma. And so what the reaction is this. So you have these two products set up, or reactants, I mean. These are going to react with each other. This will go here, there. Basically, you are forming another bridge for this one. So drawing what this kind of looks like in this form. This bridge, since there's two carbons here, is going to have two carbons on it. This will be where the new double bond is. And then how this is going to look is basically, let's see. So you have CN and the carboxylic acid group. The trick with this one is that you'll actually be able to form two products. And so while this is one of the products, the other one is just going to be, it's an enantiomer basically. And how that's going to work is basically it's just going to be the same thing, except, so you could write this in different ways. And this is basically just if the Diels-Alder happened when it attacked it from the other side. So you could have the cyano group here and the carboxylic acid group there. And that is another potential. They'd both be endo products, but because this molecule here is symmetrical, the other one isn't, you would be able to have those two potential solutions. Let's see, everyone got this next one right, so I'm going to skip it. This one most people got right as well. So I guess I'll go over this electrocyclic rearrangement problem because some people struggled with it. So this one looks kind of like this. And it said you had heat. So basically what you have to think about is kind of how this would look if it were more cyclic. And so how it's going to kind of look is basically just doing some rotating of the bonds. So you have that. And this is the same molecule, just rotated around here and rotated around here. Basically, then what this is going to look like once it reacts is this would go there, that would go here, this would go there. And so your new product will look like something like that, basically, which I drew this upside down compared to how the answer key shows it. But the correct answer was the second one that it showed, which looks something like this. I drew that backwards. And the last one goes right here. So these are the same molecule that I drew, just this is how it was written out for the answer. This is what mine kind of looked like immediately after the cycle. But either way, that's kind of what happens once you do the rearrangement. Let's see. So this next one, a lot of people got wrong as well. Let's see, describe the rotation as conrotary or disrotary of the molecular orbitals below to form a new bond. What stereoisomer will be formed? Based on the molecular orbitals shown, would you expect this reaction to occur with heat or light? So what this one looks like is it gives you this molecule here. And so there's double bonds here, here, and here. For this example, it basically has, let's see. Says this, and they drew it. So this one's shaded here. This one's shaded down here. And this is shaded here. This is shaded here. This is shaded here. And this is shaded down here. And so looking at this, based on where the double bonds are and how many nodes you would expect. So you would expect when you have 6 carbons that you would have 2 nodes. In this one, you have a node 1, 2, 3 nodes that are present. And because there are 3 nodes, you basically know that it has been excited. So this would be the LUMO, not the HOMO state. So in order to get to the LUMO state, you would treat this with light. Looking at the orientation of these, you would want to make this conrotary. So they'd want to rotate the same direction. And I forgot to add the methyl groups that were added. So there is a methyl group facing this way for both of them. So just how it's drawn, there's a methyl group facing to the left. What that means when it's conrotary is that both of these methyl groups are also going to rotate up. So they're both going to be facing up in the product. So it's going to look something like this. And that's going to be your product that's formed. I think a decent number of people. So this is one thing that we didn't really cover too much in class, but basically the difference between this being cis or trans. So if they're both outwards here from this double bond, that's when, if it's conrotary, one is up and one is down. However, if one of these is going to be in that cis conformation and they both rotate the same way, they'd both either be up or both be down. And so this all comes down to like thinking if you're looking at this head on like a clock. So we'll draw this one kind of head on. So you would potentially have something like this. And then you have a methyl group facing that way. What's going to happen then is if you rotate it clockwise, the methyl group's going to be facing up now. If the methyl group were facing the other way and it rotated clockwise, now the methyl group's facing down. And that's kind of something that really you do have to kind of look how the molecule looks in 3D space in order to draw that out. Let's see. So here's one that's just a naming one that a lot of people got wrong. My guess is, I can't see all of your answers right now, but I'm guessing Dr. Vickery will give a lot of other answers credit manually for this answer, because any IUPAC naming one, there's really more than one answer for a lot of them. So it kind of just depends on what you actually put, whether or not you'll get credit. And so this one looked like this. Some potential names that you could have put for this then are, the main one, I guess, would be 1-methoxy. Three nitrobenzene. And the reason for that is when you have two substituents, you are going to want to list these in alphabetical order. M does come before N. So this is just a methoxy group. This is a nitro group. When you list these out, you would list the methoxy first, and then the nitrate group or nitro group. And then this would be your overall name for it. As I said, depending on what you put, if it were something different, you very well may end up getting credit for it. I don't know exactly how she's going to grade it. Let's see. That's honestly most of the questions that a lot of people got wrong. Is there anything else either of you guys want me to cover? I guess here's one that a lot of people got wrong. So it was just a delocalized cloud of pi electrons in benzene is formed by the overlap of 6 what orbitals? A lot of people put sp2 for that. But remember, in benzene, the overlapping part is going to be pi orbitals, because how that works is the sp2 for the carbon, it's going to lead to, so it has a hydrogen bond somewhere. It's bonded with a double bond to one, single bond to the other. So this carbon is sp2. What that means is it has that extra pi orbital going on right now. And this pi orbital is what allows for the electrons to be shared with each other with that type of delocalized cloud. So the sp2 electrons aren't hybridized or able to, or not, they are hybridized, but they're not able to share electrons like this. Let's see. Three nitroanisole. For the one that I have drawn here, I assume that would probably work. Yeah, because anisole is one of the names that she taught you guys, I believe. So yes, you would most likely get credit for that. If you don't, feel free to shoot me or Dr. Vickery an email and I can look at it specifically after she kind of decides what she's covering, but she should count that. Let's see. So here's one that says, which of the following conjugated dienes will not react with the dienophile in a Diels-Alder reaction? And there's multiple options. And so the trick for being able to do a Diels-Alder reaction is that they do have to be in that cis configuration in order for it to work. And so drawing out some of the molecules. So this is the first one. And looking at this, so right now, this is in a trans configuration here with this double bond facing that way, this one facing that way. The question is then, can you rotate it in such a way that these are cis to each other? And because of this ring, the answer is no. So for this one, you cannot do Diels-Alder. So 1 is going to be one of our correct answers. Looking at the next one then, so for 2, that one looks like this. And so while right now they are trans to each other, the trick is though, so this one doesn't have a double bond, so it is able to rotate. And because of that, that means that this is the same thing as drawing it like this. And so 2 could do Diels-Alder, with this being your diene, so that one is not correct. Looking at the third one, it's kind of a bad drawing, but it looks like this. Once again, right now, these are trans to each other, but because they're locked in a ring, this is not able to rotate. So this one cannot do Diels-Alder, so 3 is another correct answer. And then lastly, we have this compound. And so what this is going to look like then is right now, once again, as with all of these, they're trans to each other. But since the sigma bond isn't bound by a ring or anything, this is able to rotate and equal the exact same thing as this compound actually. So 2 and 4 are basically the exact same thing, and both of those would be able to react. And so 1 and 3 aren't able to. Here's one, I guess. So it's drawn like this. That's a bad drawing. I'm going to start over. So kind of like this is how it's drawn out. And the question is this going to be aromatic, anti-aromatic, or non-aromatic? The trick for this one is regardless of Huckel's rule, looking at this, it is drawn in such a way that it's not planar. As soon as you know it's not planar, it's not going to be aromatic or anti-aromatic. So this one is just going to be non-aromatic for that reason. And once again, so if this were planar, it would, following Huckel's rule, end up equaling 8 delocalized electrons. 8 would mean that it would be anti-aromatic, but in order for it to be anti-aromatic, it has to be planar. So this one isn't planar, which means that it's going to have to be non-aromatic as the only one that works. Trying to see if there's anything else that a lot of people missed. It looks like most of the rest of the exam, a lot of people got right. Not everyone, obviously, but so if you guys have any questions on specifics, I can go from this or the part 2 of the exam. Otherwise, that's really, as I said, most of the ones that a lot of people got wrong, I've gone over. So really at this point, just up to you guys. And if you don't have any questions, feel free to head out. And yeah, whatever you guys have, my time is yours, I guess. So
Wait, did you go over it already earlier?
I didn't do the mechanism. Sorry. No. So yeah.
Okay, because I came in a little bit late.
I did the, no, I didn't do it. I did part 3 and
Oh.
4. I was thinking this is also, yeah, I can do part 2 for you.
Okay, sweet. Yeah, I think that'd be pretty cool.
Okay. So for this one, it wants you to write all the addition products for this. When it's treated with hydrochloric acid. And so basically what you're going to expect to see here is you would have, so it could add to this position or this position. And so let's say it adds here. You would basically have the chlorine here. You could also then add it to the other position, which would look something like this. Chlorine here. And those are both for kind of the 1,4 additions. I guess since it doesn't really specify, you could also have added the chlorine to this carbon, I believe, for this type of molecule, or you could have added the chlorine over here. I'll have to look exactly at the answer key to see which ones they're expecting, but I wouldn't think either of these would be favored much because they're all going to be secondary carbons. So basically there's those 4 possibilities at each of these positions. This could be dashed or wedged potentially. Then looking at how the 1,4 addition would work. So if it were at a higher temperature, you could basically then have, so you'd add the hydrogen here, that would go there. The chlorine would then be added here. The other option, and I will go over the mechanisms for these in a second. but just kind of drawing out what the products would potentially be. The other one would add a hydrogen here, have some rearrangements, and add the chlorine here would be the other option.
Oh, so we needed to do all 4 of those instead of just the 1, 2, and the 1, 4.
That's what I don't know how she's actually going to grade it, but I feel like all of these would potentially happen in certain circumstances. So my guess is she's not going to actually expect you to have all of them.
Okay.
So probably just the 1, 4 and the 1, 2, but I'll have to see her answer key and get back to you. I think really you shouldn't be expected to have all of these. And as I said, all of these then could have both enantiomers as well. So there's actually quite a few products that could have formed. So but I really don't think it's only worth 8 points. So I don't think she expected you to draw out, what would that be? Like 12 different structures for that part, especially since there's a mechanism. For which would dominate under.
You don't need to go through the mechanism. That's fine. Unless the other people, you guys want to see the mechanism?
I think it's pretty straightforward, yeah, because we've done a couple of those similar ones, I guess. So
I was just really curious about the very last one with the 2 starting materials.
Yes, okay. So that one I did kind of work through, but I will show you how that one works again because I think it's a good practice one. So for this one, basically, for the first compound, what you need to do is basically just create 2 elimination reactions. So any strong base would have worked here if you did sodium hydride or tert butoxide, whatever it would be. Just make sure I would put 2 times that. So I'm going to do tert butoxide. Obviously, any base that would allow for an elimination reaction would work here. What this then gives you for that material is you'll have this with that diene there. The other material then you do need to oxidize actually. So looking at the structure, it gives you, this has an OH here. In the product, the substituent is labeled as a CHO group. What that type of group looks like is that's an aldehyde. So we need to somehow oxidize this into an aldehyde. One way to do that is with PCC, anything like that. You've learned a few oxidizing agents in the past. As long as it's one of those, you'll basically then oxidize this to an aldehyde. And that's all you actually have to do to both of those starting materials. So right now, if they participated in Diels-Alder, they would form that desired product. And that's all it comes down to. It shows the endo product as well. So you don't need any changes with that. It's literally just you have 1 step for each substituent. You'd put those together and then form your product. Does that make sense? Do you have any questions?
No, yeah, that makes sense. Thanks. Appreciate it.
Cool. Yeah. And as I said, that's kind of about all I've got. There's obviously 10 minutes left. So if any of you showed up late and want me to go over anything else on the exam, feel free to put it in the chat or let me know. Otherwise, yeah, that's kind of all I've got planned for today.